Hi, it's me, Tim Dodd, the Everyday Astronaut. I try really hard on this channel to not, be too hyperbolic. I don't want to overuse words like groundbreaking or game-changing or even novel because, frankly, there's very few things in the aerospace industry that are truly any of those things. So when a small company based out of Kent, Washington reached out to me claiming to have a fully reusable, groundbreaking, novel rocket, I was obviously quite skeptical. So what if I told you there is a small little rocket company that you likely haven't heard of that is not only claiming all of these crazy things, they're already building it and testing it at, frankly, a ridiculous pace. And best of all, at least to me, they're utilizing the Aerospike effect in a genius way to help make a fully reusable upper stage. So today I'm going to show you around Stoke Space's headquarters and their test facility to help reveal their super unique rocket. I'll explain in great detail how it works from their actively regeneratively cooled heat shield to its unique offset geometry for precision reentry and landing, but also how its awesome engine is integrated into that heat shield. And best of all, we're actually going to see them fire up this incredible engine. And that's not all. Stick around to the end because their CEO, Andy Lapsa, dropped a bit of a one more thing on me with a little detail that I couldn't believe. There's a ton to talk about and see, so let's get started.
3, 2, 1, that's one small step for man. Contact with a test one.
Hey Tim, come on in.
Hey, how's it going?
Good, nice to meet you.
Nice to meet you.
Let me show you what we're working on.
Sweet. So I feel like I gotta kind of learn about how you guys are even doing this because I don't have even the slightest clue on what you guys are working on.
Well, let's do it. Let's get into it. Yeah, so this is what we're building. In some sense, it's a traditional two-stage to orbit, vertical takeoff, vertical landing. First stage looks very familiar to what the industry has shown already.
Yep.
Second stage goes on orbit. Deploys spacecraft, can do a number of things on orbit, can move around orbit, can acquire assets on orbit, and then can bring them home. The reentry is more or less a capsule-style ballistic reentry, although we do have cross-range built in, and then we can do precision landing. The engine has to do a lot of things now that are not typical for upper stage engines.
Right.
It's got to obviously do the deployment mission, but it's also got to do the reentry burn and then terminal descent in atmosphere.
Yep.
So it's got to throttle deeply. It's got to work inside the atmosphere. It's got to work outside the atmosphere. The engine's got to do a lot of things. So that's why it looks weird.
Yeah. And I'm self-spoiling here, but based on being an in-space engine and a sea-level engine, I know there's only one engine that can kind of do that. Why don't we go take a look at all the stuff because I think there's probably a lot of things we'll probably learn seeing it up close.
Awesome. Let's do it.
There's some hardware here. Oh man. Okay, you weren't kidding. There is hardware here already.
Yeah, so I mean, that's the name of the game is design, build, test, iterate as fast as you can possibly do it. And to do that quickly, you've got to be vertically integrated. You got to own your dependencies and be able to move as fast as possible. So we tried to build that capability up as fast as we could. Everything you see, we've built in about the last 18 months. We're definitely already out of space and using other space to play Frogger with different parts and
Different
stuff. But this is our serial number 2 engine build. We'll see, I guess, the business end of it in a little bit. It's pretty cool.
So, if you don't mind me asking, as we're kind of looking at the actual hardware here, like what are, those are struts to hold what?
These are the thrust takeout.
Oh, okay.
One of the cool things about this design is, you think about thrust being generated and then how it works its way up the vehicle. All of that thrust load has to make it to the outer skin of the vehicle and goes up basically through the tank structure, right? So one of the cool things about this architecture is the thrust is already distributed around the perimeter.
Inherently.
And since we don't have to gimbal the engine, like if you gimbaled the engine, you'd have to bring all that thrust load into a center point and then redistribute it all out.
Yep.
Structurally, it's very inefficient.
Yep.
So here we got the thrust all the way on the perimeter and we keep it there. So our thrust takeout is little tie rods. That's all
Wow.
it takes.
Huh. And curious why they are not rigid. Why are they? Why do they
Well,
move?
they become rigid, right? So when we get up
It's just
to,
for installation that they're on bearings and stuff.
Yeah, it gives you
Okay.
the small little micro adjustments that you need in order to
Precisely.
true in. Right?
Yep. Got it.
Yep. And then it's on bearings. Okay, it's on bearings because this is designed to take a linear load.
Mm-hmm.
It's not designed to take a moment or a torque.
Right.
So you put it on bearings to eliminate any torque.
Gotcha.
Otherwise, you damage the.
Gotcha. Yep. Yeah. Even a degree or two of
Yep.
torque. Gotcha.
Yep, exactly.
Okay. So 30 thrust chambers, right?
30 thrust chambers.
That's
wild.
wild, honestly. So which side of it will the turbo pump hang off of here?
I
to tell.
believe at least the way
the-
it was clocked on the last build, it's over there.
Okay.
Yep.
Yeah, you can kind of see, well, maybe a little bit more. Over
I don't
there.
know if you'd have anything to be able to see it at this phase.
Okay. It looks like you got kind of a QD connection over there. So this is the one you're building to hop, right?
Yep.
So you're already getting to the point of having to have disconnects, or no, you'll probably keep it tethered, right?
Nope.
You're going for it already?
No tethers.
No.
Yeah.
Holy cow! So you're already looking on your second one to have you have to develop your QD and everything.
Yeah. I mean, the nice thing, it's such a modular design that it will be our second formal build, but parts can go in and out of it all the time. You
Okay.
know, so we've been doing that on the engine on the stand. We've got, I don't know how many pumps have been on and off of that stand as we, continue to dial things in, but it's very modular.
Wow.
Yeah.
Wow. It's big, and that tank. Can we check out the tank? here?
Yeah.
That's big. Oh, and so it does taper.
It does taper.
It's not.
This is the real deal, man.
It tapers, and so your heat load is. You shouldn't really be experiencing too much heat. It's kind of like a capsule, like a traditional.
Yeah.
Your second stage is almost like a traditional capsule.
Yeah, that's the idea.
Crazy.
Make it a traditional capsule, base first. That's where you take all the heat load of reentry. And that minimizes the amount of surface area that you need for whatever your thermal protection system is. So we do that. It has some other nice byproducts of this. One of them is all of the inertial loading is in the axial direction, both on the way up and on the way down.
Yep. You don't have to have
Right,
it. It's
so
not
no-
coming in horizontal or anything and having to do.
Yeah. So that's nice if you're a payload. It's nice you don't have to deal with the change in acceleration vector. It's also nice from a structural efficiency standpoint on the vehicle. You don't have to design for those transverse accelerations.
Yep. That's actually something that's being talked a lot about topically right now on Twitter is SLS out on the launch pad with the hurricane coming in.
Yeah.
People are going, why can it only, it's going supersonic. Why can it only handle 85 mile an hour winds? It's like, that's in one direction. It can go, it can handle a lot of dynamic pressure. It's not meant to have high wind shear forces coming in from the side of the vehicle.
That's right.
So this is the same thing almost. It's not meant to ever fly horizontally. It's always going to remain vertical.
Yep. So that's some of the structural efficiency that we gain. Not having gimbals is another element of structural efficiency that we gain. And so kind of as you go through the system, there's these little pieces that allow the system level solution to be pretty highly efficient, even though you've built in what's traditionally thought of as pretty heavy architecture for the engine. We're able to do it in a mass that makes sense for an upper stage. It's pretty cool.
So so during reentry, are you actually going to be flowing cryogenic fuel through the walls of the heat shield and everything, or how does that?
That's what it is. It's
That's what
actively
it is.
cooled, right?
And how does it? What pressurizes that? Like how do you keep it flowing?
Same circuitry that runs the engine.
So do you actually have to spool up the turbo pump a little bit to keep it moving? Really?
But, I mean, it's an expander cycle. So you get, instead of taking the energy out from the chambers, you take the energy out from the heat of reentry.
The heat of reentry.
And it
And it spins itself.
powers
and
itself up.
No, okay. Okay.
Yeah.
That's really cool. That's really, because people always ask, like, why don't they capture that energy? And that's basically what you're doing. You're capturing energy to power a regenerative cooling structure.
Yeah.
Okay, I love that. Okay, let me take a second here and explain why this is so cool. Stoke's upper stage engine is using the expander cycle, which, as those of you who have watched my how to power a rocket engine video may know, it's where you take the heat from the engine to heat up the fuel so it changes from a cold and dense fluid to a high temperature gas-like fluid, and then that now hot, high pressure gaseous fuel will flow through the turbine to power the pumps. It's a very cool system since it uses what could be just wasted heat energy, it recaptures it and uses that to power the pumps. But the same principle is being used here for the heat shield. So basically, after exiting the pumps, the fuel will flow through the heat shield into the combustion chambers, and then some of it goes back to power the turbine, which powers the pumps before being dumped overboard. So on re-entry, as the vehicle comes back into the atmosphere, it compresses the oncoming airstream so much it'll heat the air molecules up into a plasma, and you have to deal with that extremely hot re-entry heat somehow. So instead of a traditional heat shield that might ablate, or basically flake or intentionally burn to take heat away with it, or a strong insulator like the silica tiles on the space shuttle, they're going to flow some cryogenic fuel through the heat shield to cool the metal down, similar to the regenerative cooling inside the combustion chambers of the engines. Now the beauty of this system is that because it's an expander cycle engine, this heat shield can more or less self-regulate and power itself. As it heats up, it'll heat up the fuel inside it, and then that will flow towards the exit after flowing through the turbine. The turbine will spin, which will spin the pumps and begin to move more propellant through the heat shield faster. The hotter it gets, the more fuel will flow through the heat shield and through the turbine, which will then increase the speed of the pumps and increase the flow rate of the propellant into the heat shield to cool it off more and more. It's truly a genius double use of the system. The engines won't light up during this because the fuel is being routed through the turbine and none of it is going into the engine injectors and into the combustion chambers for this phase. So the fuel is only being used to cool the heat shield and the combustion chambers and then used to power the pumps. But then during the landing phase, obviously they'll go back to the normal routing of fuel, which will have some of it go through the turbine to power the pumps, but the majority is routed into the combustion chambers along with the liquid oxygen through the injector to actually power the engines to propulsively land, and we'll talk about that more in a second.
So, I mean, I actually have not seen that in the literature before. You have seen, there are a couple different ideas. Everybody tried everything in the 50s and 60s. I think we're in like this Renaissance period where people are actually having ideas and then building stuff.
Yeah.
That died for a while, but in the 60s, for a long time, I was like, man, every good idea, not only somebody already had it, they already tested it, right? If you dig deep enough, there's test data on everything.
I know. Yeah, that was a heyday for sure.
It had been proposed, different active cooling solutions have been proposed. Water is a, attractive candidate for a couple of different reasons, but it requires totally separate circuitry, new tanks, new pumps, new pressurization systems, and it's all drag-on mass for all of the rest of phases of flight. And what this does is gets rid of all that drag-on mass where you're actually using it for every phase of flight.
Yes. Right? You're the same thing that makes it go up allows it to come down.
That's right.
That's amazing.
Yeah, and if we couldn't find that solution, I'm pretty sure this wouldn't make sense.
Yeah. So, and another thing too, you're not doing like transpirational cooling or anything. You're actually just keeping it all, inside the coolant lines, right?
That's right.
Yeah.
That's right.
It could, like you said, it could become transpirational cooling if there is an issue with it.
That's right. If you get like a little micro crack or something, then it does, and it overcools, and it just keeps going. Just keeps going.
You might want to fix it for the next flight, but it'll clearly survive re-entry.
Yeah, or, I mean, honestly, maybe, but you don't fix every little micro crack on an airplane wing every flight, right? You have scheduled maintenance, you track those things, and
you have acceptable bounds of what is. So, wow.
That's all high quality problem down the road, right? Where you start to deal with those problems.
Yep.
Which is cool.
Wow. So is this stainless steel?
Stainless steel.
And what drove you guys? Let's get a little different shot on this here. Let's walk around a little bit here.
It might be cool on the forward end also. I mean, we can.
What drove you guys to do stainless steel instead of carbon
By the way,
composites?
you asked about the tie rods, so these are the tie-ins for tie rods, right?
it's upside down, isn't it?
It's got
Yeah.
turn 90
okay,
degrees,
okay, got it.
Yep.
Okay, that makes a lot more sense now. Okay, so what drove you guys to do stainless steel instead of anything else, aluminum or carbon or?
Well, I would say that our single decisive reason is manufacturability.
Yeah.
And availability of material, right? So
Yeah.
especially these days where you do have supply crunches, everyday stainless steel, we can source that, no problem. Sheet metal is amazing. It comes to you, first of all, it's commoditized from a number of different suppliers. It comes with amazing material properties out of the gate. Thin-walled pressure vessels like to have good material properties. And then from a workability and manufacturability standpoint, almost nothing beats it, right?
Yep.
So those are reasons. The question then, what is the mass impact, et cetera? And you can basically polish a turd on that, and analysis will produce, garbage in, garbage out, or inputs determine the outputs, right?
Yep.
So there's a number of ways you can look at it, and our standpoint was like, okay, it's a close enough trade, we're just going to optimize for manufacturing.
Yeah.
And that's what we did.
And
the other thing was stainless.
You could spend years and gobs of money just even trying to figure out which metal to
That's
choose.
right.
Like at the end of the day, you're chasing a couple of percentage points or whatever.
Yeah.
Okay.
Just go build.
Yeah.
And the other thing I think that's worth mentioning on the upper stage is it's coming in, the skin will get warm. Stainless holds its material properties at much higher temperatures than like aluminum.
Yeah.
And one of the things that I think is really cool about our architecture, being actively cooled, it's going to come in and land. It'd actually be cold, not hot, right?
Yeah.
But like if you look at shuttle came in, those tiles, it's passively cooled.
Yep.
Yeah, that protects it during reentry, but it's also absorbing all that heat.
Absorbing all the heat.
And that heat over time is soaking in.
Yes.
And they actually had to plug in a water coolant circuit in order to protect the aluminum structure from losing material properties as the heat soaks.
Yep.
So when you think about how fast can I approach the vehicle to service it or start getting ready for the next mission, you got to deal with, like ceramic tile solution has to deal with all that.
Yeah.
Yep.
Well, and like you said, stainless steel can handle pretty high heat loads. Like Centaur upper stages have survived intact, and made it back through reentry in one piece, which is crazy. That's really thin too. That's really thin with no additional consideration for reentry, and obviously you guys are going to be having
pieces of it.
Yeah, pieces of it. Yeah, pieces of it. Yeah, that's true. Yeah, not completely perfect, but so you guys are going to be having still another layer on top of this that is your active heat shield /
Yeah. This is just tank dome. Engine, that assembly is installed, downstream of that, and then we'll go. I can show you the heat shield. Let's go look at it.
Yeah, sweet.
Okay. So this is our heat shield. It, you can see the shoulder of it is the ring that you see in our hot fire videos. These holes are cutouts for the thrusters. And then the rest of this is designed to enclose really all of the vehicle systems. So the turbo machinery on the engines, valves, pressurant bottles, avionics, controls, all of the things it takes to run the vehicle are all kind of housed in a volume between the heat shield and the tank dome.
And that tank dome.
Right?
So the bottom tank, is that your fuel tank, or is the bottom tank the oxygen tank?
Yeah, and then similar to Starship, we do have, they call them the header tanks, we call them the landing tanks, but tanks inside tanks to do different phases of flight.
Okay.
We didn't talk about it. Okay, so we were talking about the kind of the cool things about going up and back base, well, nose first and base first.
Yep.
One of the things that's nice that we avoid is the cryofluid management of the swan dive maneuver, right?
Yeah.
It's one of
It's
the
all
things
flowing in the same direction always, in the tanks
always,
in the same.
inertial loads are always in the same direction. Pumps are being primed nicely, right? We kind of avoid that challenge, which, is solvable. Starship is solving it. They did, right?
Yep.
But when we were architecting this in the basement, we're like, oh, that seems like a hard problem. We don't want to do that.
Yeah, exactly. Okay, so all your loads are going to be the same. Fluid transfer loads, everything is flowing in the same direction. Throughout reentry and lift off, which is huge. So obviously you must, okay, so I'm trying to figure out, so the gapping, so there is that much space between the bottom of the bulkhead and the bottom of the dome, and enough room to put a turbo pump and all your landing tanks and COPVs, avionics, all fits underneath this heat shield, well, I guess above the heat shield between the bottom dome.
Yeah. Yep.
It seems like a really tight package.
It's an aerospace vehicle. I mean, if you ever climbed in the wheel well of a 737 or something, there's a lot jammed in there, right?
Yeah.
Yeah. So.
Dang. So, is this actually actively cooled already? Mm-hmm. Is there so it's the channels through here?
Yeah, you can kind of see, you can kind of
Oh.
see the channels in the shoulders, and you can see them, different grind levels, right?
So then at the top, what's happening at the very middle there?
So it's an open expander. So you got to do something with the turbine drive gas.
Yep.
And so this is where, some of the nuances of the Aerospike come into play, but one of them is, if you read the, whether it's the J2X or the X33 engine, performance is actually better when you have some amount of base bleed.
Yeah.
Right?
Yeah.
So the Aerospike architecture actually lends itself quite well to an open cycle.
Yep. Yes.
Okay.
You
so
want to fill that
yeah.
little wake, I believe.
So that hole is turbine exhaust.
Oh, it's almost getting to this point of why, like I'm starting to the point of going, why hasn't this been done before?
I don't know.
Because it almost seems all so.
Let's see if we can do it.
Wow. Have you ever considered the option of, before you worry about developing your own booster, just flying the upper stage on somebody else? And
It would take some doing. One of the reasons that we are fully vertical is that interface is non-trivial.
Yeah.
There's not a whole lot of companies working with hydrogen, although we actually do have a fully mobile hydrogen infrastructure, because we're going to fly Hopper, right?
Right.
It's already mobile. It already fills up the tank, right? So we can do it, but the interface is pretty non-trivial, right? So we know we want to go there anyway. It's the right move for efficiency, so that we're just focused on doing it that way.
Wow. Okay, I can't wait to see this thing fire. That is amazing. And I'm a little bit confused. How do you get from? Sorry, I'm just trying to get this all together in my head. At what point is this only always your bleed line coming through here?
Okay, so bleed comes out the hole, but the feed is all going from center outward.
Center
so
outward.
This is all like liquid or cold hydrogen.
Okay.
That eventually feeds the nozzles.
Through the nozzles.
And drives the pumps.
Okay. And where I'm trying to, like, the manifolds that we see where the chambers are, is this replacing that, or is there another one behind it?
Nope.
So that was just a test stand.
Yeah.
Okay. So and then the additional bit of expansion that we get
you
here.
can think of that thing as, the other side has a higher sidewall, right? But
Yep.
that thing is like a slice of 3 of these thrusters.
Yep. And now it's just cantered in
And
to
now it has
begin a
some-
radius.
Right.
So, and then this is the little extra bit of expansion that we gain, is from here to here, out of
The expansion that we gain is from here to the other side.
to the other side.
All of this it's not a high pressure, but it is a pressure. So all of this is providing thrust in space. There's pressure against this whole
All of
surface.
it. That hurts my head.
That's the Aerospike.
That's the Aerospike. But in my mind, an Aerospike always goes like, it's just the actual walls.
The sidewall has this, this very optimized contour,
Like-
blah, 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 blah.
Yeah.
Right? And that doesn't make sense for the reentry phase, right?
Right.
This whole thing is not how do we design an Aerospike. It's how do we bury a second stage engine into a heat shield.
Into a heat shield, yeah.
Right?
So what happens inside the thrust chambers during reentry? Does the wake kind of come?
It's cooled too.
It's actively cooled too.
So you just basically deadhead it.
Yep.
We've got stagnation gas in there,
Yep.
but the walls are actively cooled.
Walls are still flowing. So they're basically a heat shield themselves. They can already handle the internal temperatures of combustion. Handling reentry temperatures is a walk in the park.
I hope.
Holy cow. This is getting more and more, just the more I'm thinking about this, the more why hasn't this been done before? It's so cool. And I love the canted angle, or I don't know how you describe it, the skew of it, so you can have, it's like a very exaggerated blunt body reentry that you would normally have on a capsule. So you actually can provide a fairly healthy lifting vector from not a wing, and it's still your heat shield. It's still your, it's just like everything is something else.
Yeah.
That should be the name of it. That should be Stoke. Everything is something else.
I like it.
I like it. That is just so cool. All right, what else do you have to show us here? Let's interrupt again here real quick to explain how they can precisely steer this thing without using wings or fins, and instead they can just use the offset in the mass and the offset in the heat shield to provide a lifting vector. This concept isn't new. In fact, pretty much all capsules have their mass offset from the center of the capsule, so they can do exactly that, steer and control their re-entry to some degree. In fact, the Orion capsule on Artemis 1 did a fair amount of trajectory correction in the atmosphere during its ballistic skip re-entry. If you have your center of mass offset from the center of your heat shield, there will be a lifting vector that's perpendicular to the direction of travel on one axis. Then by rolling the capsule, you can actually steer it. This is especially useful for raising or lowering your trajectory to extend or shorten where you'll land downrange. And by rolling it on its sides, you can even steer left or right too. But Stoke took this a different way. By having a pretty major skew of their heat shield, they're able to get a similar lifting vector like a capsule, but with a more cylindrical body. But they can still provide the steering authority to be able to precisely target their landing site. This means they don't need any additional mass for aerodynamic control features, just the offset and the skew of that heat shield. Then they can just use the reaction control thrusters to roll for steering, and it should be able to precisely target its landing site.
This is our little machine shop. We've got the capabilities to do most things. 4-axis, 5-axis, lathe, mill, got chambers up here.
That's a fresh chamber coming out of there.
Chamber.
There is a brand new baby being born into the world right there.
Yeah.
And was that being CNC'd at this point?
Yeah.
Jeez.
Yeah, so it comes out of print. I mean, you're familiar with the process, but it comes out of print. In fact, you probably have some raw prints back there. And then all of the sealing surfaces and mating interfaces and things like that always need still final machine, right?
Yep.
So
That's,
what we're doing.
I love it.
Mating machines in the back who do EDM. You're familiar with EDM? Got EDM in the house.
So then that gets machined down into your final thrust chamber. And you're using copper lined thrust chambers. What's the exterior? What's the exterior of the chamber made out of?
It's just copper.
It is copper too.
Low pressure, so
Oh.
you don't need a huge structural jacket.
Right. Okay. And there's another thing. It's like, dang, you don't have to do the fancy, meddling of bimetallic stuff.
Right? That's still a tough nut to crack.
Yeah.
Right?
Yeah. Wow. Low pressure. The low pressure thing is coming around as a.
Well, it's everything, right? It helps the open cycle be more efficient because you don't need as much energy to drive the turbines.
Yep.
Again, as long as you can get a giant expansion ratio.
Right. Unbelievable. I mean, the scale of this thing, it's not small.
It's not Starship, but it's not small.
No, it's not a Starship, but it's not small. It's not small at all. That's it. And how tall is your vehicle going to be when it's all fully stacked?
100. A little bit less.
Wow. That's 100 feet for those of you in America. Yeah.
30.
Yeah, 30 exactly. Yep. Wow. And 12 feet, so that's what, like 3.7, yeah, a little more. And it tapers, so your booster's actually a little bit skinnier than your upper stage until
Booster's skinnier and then it tapers out.
flares out a little bit. Does that booster design help during re-entry? Does that booster actually help the flare? Yeah, or is that?
I mean, so you're familiar with having the grid fins out there.
Yep.
That moves center of pressure back and gives you the control authority. But yeah, that taper moves center of pressure back.
At least at subsonic regimes, I'm sure. Probably not a lot during hyper or supersonic. Yeah. So that probably helps have a slightly slower terminal velocity too. Yeah. Cool. Do you have an aerodynamic control surface for the booster?
It will, yeah, I mean, you've got to drive it to precision landing. So
Yep. Yeah. Are they going to be canards or grid fins?
Not canards.
Not canards. Grid fins though, or some
Yeah.
cool. Yeah. Yeah, I still like how, and maybe you don't like it, but I appreciate how Blue Origin had the ring on New Shepard. I think that's a really cool little design because it acts as a ring stabilizer and has the room to pop out those extra fins and everything. It's a pretty slick little thing.
Yeah.
Yeah. And I like.
Cool vehicle.
It really
and
is.
It's, from a stability perspective, Jeff's talked about it on record, but from a stability perspective, it's short and stubby, so it's
Right.
a non-trivial problem to solve.
Yeah.
That thing to fly forward and back.
Yep. That's pretty cool. And yeah, this almost seems like that taper just sort of reminds me of that. And I always thought that design was really cool.
Yeah.
You know. Yeah.
Yeah, I mean, you were talking about it for high altitude flight. Like on paper, rocket equation, this thing can go to 400,000 feet.
Yeah.
We were really excited about that.
Yeah.
And then once it came down to actually designing that mission, we're like, oh, well, we got to add this, that, the other thing, or change the OML, the outer mold line. And then we're like, that's a whole new vehicle.
That's a totally
We'll just fly it.
Yeah. Just do short hops and not worry about actually getting it up to speed.
Yep.
That's
There you go.
amazing. Wow. Well, is there anything else that you can think of that
Well,
we can
I was going to
see?
say, if we go off camera,
Yeah.
we can walk through turbopumps and chambers,
Yeah.
show you those things.
Yeah. And we can talk about them off camera. Yeah. After a little tour of the secret sauce stuff that unfortunately I legally can't show you, we packed up and headed out to Moses Lake, which is about a 3-hour drive from Kent. This is where they have their test stand and where they're currently testing their first developmental engine. And best of all, they were priming the engine by the time we got there. They were getting it ready to do a test fire for us while we're there. Well, first off, where are we right now?
We're in Moses Lake, Washington. This facility we've built up really from scratch in the last 18 months or so. Moses Lake is a really cool small town, eastern or central Washington, that has a surprising amount of aerospace and kind of technical community around it because some old military work, Boeing and Air Force use it for different trainings and test flights. And it's got a humongous airport, which is right over there. Or at least the runway is humongous. It was actually a backup shuttle landing site.
Really?
Yep.
No way.
So there's a lot of infrastructure in the town, which is really cool, and talent, and it's a great place to build and test.
That's awesome. How far is it was a 3-hour drive out here.
About a 3-hour drive, yeah. So
are there any flights that pop down into here from SeaTech?
not commercial, but when you start flying around on a jet, you can land yourself.
Hey, maybe someday. Someday. But we're
So we wanted a test facility as close as possible to engineering and manufacturing, and it's a 3 hours drive, which takes some time, but it's not a plane ride, it's not a time zone change, and we shuttle parts back and forth every day, just about.
Yeah.
So helps our speed and iteration.
So that's it.
This is our second stage stand, yeah. So it's designed to do engine testing like we're doing. We can also install the vehicle itself and do hold down tests up there, the full
cool.
vehicle.
Yeah.
Want to go up and
I do.
check out the goods?
I was already itching. I'm like, I got to see this thing up close. Now, I think one of the crazy things for me, this is a cool shot. Just looking up underneath here. Look at that. Oh man, that's what's crazy is from here you can't even see there's the turbo pumps. Oh,
yeah,
they're
pumps
so
are kind of
cute.
Yeah, aren't they cute?
They actually really are. I mean, honestly, like they're just wow. That's amazing that those guys can power the whole thing.
Yeah, the fuel pump's about 1,000 horsepower.
Yep.
And fuel pump or aux pump doesn't need as much power, but turbo pumps are amazing. There's just tons of power packed into a small little volume, right?
Yeah. And what's amazing to me is that you guys are brave enough to use hydrogen, which frankly is kind of rare these days,
Yeah, it's not in vogue at the moment, but look, I think for what we're trying to do, it's absolutely the right propellant. It has amazing efficiency, specific impulse, gives us the elbow room and performance that we need in order to perform these reuse functions with the upper stage, right? You think about Earth and how kind of lucky we are to be able to escape Earth's gravity well with chemical propulsion.
Yeah.
We can do it.
Yeah.
But it's like right on the
I
edge,
know,
right?
we're lucky. If it was like 5% more, even a little bit thicker atmosphere, it'd just get that much nastier. We're
Yep.
just at the cusp of like, it's doable, and then it makes it a lot harder when you're trying to reuse everything. you know,
Yeah.
that's
Yeah, so that's the
definitely-
thing, right? Like every pound that you put on the vehicle that has to be dedicated for reuse is a pound that you can't use for payload. So there's kind of two things you can do. The first thing that you can do to build in the margin that you need to reuse is use like massive economies of scale, which is what Starship is doing, or you have to find elbow room somewhere else, and we find that with hydrogen it gives us enough extra performance.
But you don't find it to be too cantankerous to handle?
No,
and-
it's definitely a specialty skill set, but I think as with anything, with practice, you can get good at it. So we have a team that's operated hydrogen before, and the new people we bring in now have that expertise also. And we've run, a month of October, we ran 70 engine tests with hydrogen. So
In the month of October, you've run 70 engine tests.
yeah, now we're
So over
they're
twice
short
a day.
duration, and and that's average too. So test days will run more, and then we have build in some down days for. Look, we're also in an active construction zone, as you've seen. So we've got
Yeah.
other activities we've got to do too. So there's a lot going on.
That's just hard to. I feel like, I don't know. Maybe this is the old school aerospace thinking in me, but like I feel like hydrogen is just so nasty that people are lucky to fire up their engines a couple. It just seems like it's just so finicky, and people are so afraid of it now. And of course, right now, topically, like SLS and the Artemis program is, had the woes with hydrogen already. But I also don't think they're firing the RS-25 off on average twice a day. No, I don't think.
Yeah.
I know they're not firing the RS-25 off on average twice a day.
I think it also depends a little bit on where you're at in the development schedule, but I think practice is number one. Practice and design to be able to do this is the most important ingredient, and then you have to be able to accept a wrist posture that allows it, right?
Yeah.
But yeah, you design your systems and your safeties in place, then it works.
Yeah. That's amazing. You're going to try and see if we can light this engine here at the upper
Yeah.
stage engine for us.
Yeah, we'll try to get a test out for you.
Here we go.
There we go. There we go.
Yes!
That was awesome.
Yes!
All right.
That looked great. That was like
Yeah.
seeing all the little thrust chambers.
Isn't that wild?
That's so cool.
wild.
I've never been next to an engine that just fired so recently either, man. This is
Yeah.
crazy.
So this will just be basically boil off as the run lines upstream of the, these are the ISO valves here. So it's just boiling off and venting. That's what I was talking about. Like that heat shield coming in, we're actually more worried that it's gonna be cold instead of hot, right? So
Yeah.
it's pretty cool.
You can imagine now.
Hydrogen is absolutely the right answer, I think, for our upper stage and what we're trying to do with it. But it is a little more expensive from a cost perspective. a little bit harder to source. And so when you think about rapid turnaround and rapid reuse, you know, the less you can use, the better. So that's one thing. And then the other thing, the big thing is density, right? Hydrogen is just really, really low density. So when you use it for a booster, the booster becomes huge and you know, physically large, and that's less optimal for quick reuse and operability perspective. So we use methane. It's about as cheap as you can possibly get. Burns super clean, and you know, I think it's the right answer for rapid reuse booster engines.
Yeah. But what about and then the engine itself? You know, you're using a more conventional set of engines, it looks like, for your first stage.
Yeah, so here's the thing, the weird, it's gonna be maybe weird for me to say it, but an Aerospike is just not the right answer for a booster engine. If you want high performance out of the booster, the right answer to me is a closed cycle booster engine, and you know, you turn up chamber pressure and make it operate, you know, that way. As you scale up Aerospikes, they just don't actually scale well.
Yeah.
Right? Like you can't, the advantage of an Aerospike would be if you could get really high vacuum performance, then maybe they would win, but they only get you, what, 10-15% mission average ISP benefit?
Yeah.
Something like that?
Yeah.
And they want to be an open cycle. So just by moving it from an open cycle to a closed cycle, boom, you get that.
Yeah.
Right?
Yep,
And then
there
the
that
second
is.
thing is, in vacuum, the higher performance comes from a high expansion ratio. So you can get that with a regular bell nozzle by turning up chamber pressure. In order to get it out of an Aerospike, you have to make the diameter of this thing wider.
So you can have a longer spike to work with?
Well, so like the diameter of the Aerospike translates to the
The overall
expansion
ratio, yeah.
you know, the nozzle exit
Yep.
area, right?
Yep.
So to make it a higher expansion ratio, you make it a higher diameter. But the expansion ratio is throat area to exit diameter, right?
Yep.
So the throat area has to be the same as you're making it wider diameter, which means if it's an annular throat,
Yep.
the throat gap is getting smaller and smaller and smaller. Okay?
Oh.
So when you get to like reasonably big expansion ratio, like even like 100, 150, 200, whatever it is, right? That throat gap is like
Literally
thousandths
becomes
of an inch.
Tiny.
So try imagining trying to hold those tolerances in fab. And if you're off by 1,000th of an inch, but your whole gap is like 3,000ths of an inch, then you have a massive thrust imbalance from one side to the next.
Whoa.
So it doesn't make any sense.
Right.
So you're gonna discretize these throats anyway into circular thrusters like we have.
Yep.
They're gonna be all these tiny little guys. It becomes like massively complex. So
Wow.
it's kind of weird. We did wind up with an engine that uses the Aerospike effect, but it is not designed like you would see a classic
It's not like
Aerospike.
it's not like you designed you went out to make an Aerospike and that was your solution. It's more like your solution was reentry and landing, and then it's like, oh, I guess it's an Aerospike now.
Yeah, I mean, that's exactly what it is. We kind of started with this thesis of the actively cooled heat shield. We thought about, you know, what that vehicle looks like in that context. We wanted to come in base first for various reasons, partially because that makes sense for the actively cooled heat shield. And we talked about the axial load in both directions, you know, blah, blah, blah. So the major technical problem for us was, all right, that all makes sense, but how do you bury a high-performance second stage engine into a heat shield?
Yeah.
And we went through all kinds of different designs that were not Aerospikes.
Yep.
And finally landed on this design that, again, it's not a classic Aerospike. It does make use of the Aerospike effect, but
I love it.
that's how we wound up. But yeah, it doesn't make sense for the first stage.
Can you run me through, just run me through the whole startup process of either this engine or just a general engine, because you obviously worked on a handful of engines. So walk me through, make sure I'm not missing anything when I'm talking about engine startup.
Well, I would say first of all, globally, the start transient and to some extent also the shutdown transient are some of the highest risk moments in a rocket engine, right? And if you think about it, like our little engine 1,000 horsepower in the pumps. Bigger engines have tens of thousands of horsepower going through the pumps, and they go from 0 to full power in maybe a couple seconds, right?
Yeah.
So you've got to control all those horses and make sure they're running in the right direction during that time. So in early development, it is usually one of the higher risk activities for a rocket engine. And then the actual transient is pretty highly dependent on the engine cycle that you're running, right? Mm-hmm. So I would just say that, as you're working through these processes through development, there's cases where if certain things are not right, like the pump is also doing a lot of work, right? So one end of the pump, turbine end of the pump is generating power, pump end of the pump is consuming power, right?
Yeah.
So when we say 1,000 horsepower pump, by the way, one end is generating it and the other end's consuming
Yeah,
it. So
it's it's all right there.
it's like 2,000 kind of, plus 1,000, minus 1,000.
Yeah.
So it's doing that work, and if that's not balanced, if the amount of work you're asking the pump to do outweighs the amount of power you're giving to the turbine, then yeah, it goes the other way and doesn't bootstrap, right? So you've got to work through all that and keep it all balanced.
And then what's your actual...
And by the way, it also has to happen on the oxygen side, and those two have to stay in balance because they're coming together and joining in the combustion chamber. So it's a dance.
It is a very delicate dance. So then what's your actual ignition process? How do you actually light the chambers? What's the process?
There's a number of different ways to light it, but it's a fire triangle. So you got an oxidizer, you got fuel, and you need a heat source. So you can get that heat source through either a pyro, solid, propellant. You get it through a torch, you can get it through a glow plug, get it through a spark. So there's a number of different ways. We use one of those.
Yep.
And really trying to put that system through the ringer also to make sure it's reliable. And one of the cool things that I guess it's obvious when you think about it, but every single test we're doing tests 15 of these systems at once. We're racking up, if you rack up chamber test time, we rack that up
15 times faster than a normal program.
And
that could be seen as a totally bad thing, but at the end of the day,
at the end of the day, it's got to work, right?
Yeah.
Like, look at Starship. It's got a gazillion engines, right?
Yeah.
And if you beat the crap out of these things enough, then you work all the bugs out, and they're reliable.
Yeah.
So they've got to work anyway. So that's true for accumulating test time. That's true for part-to-part variability. That's true for all kinds of stuff that we see. And this rework that we're doing today is a great example. We just run as many tests as possible and iterate and fix the bugs as we go.
That's so cool. So obviously, you guys using expander, you don't have like a pre-burner type of injector, so you really just have injectors in each of the chambers here, though. You have a handful of injectors, 15 for now, 30 in the near future.
Yep.
Walk me through your injector choice solution. How did you end up with what you ended up with?
I guess the first thing is that each of these, the way we control the vehicle, we don't gimbal the engine, right? It doesn't swing. Which, again, how do you fit a high-performing upper stage engine into a heat shield and make that robust? Yeah. Originally, we were gimbaling it, and similar to the ceramic tile question we had, when you get into a hot gas dynamic seal that's reliable on flight 100, we're just like, no, we're never gonna trust that.
Right.
So we designed out the gimbal, and the way we steer the vehicle is by basically individually throttling the thrusters. So that feeds into, kind of the rest of the design, and you've got to pick an injector that's able to do that. Yeah, so we're using a Pintle on these guys. It does a lot of what we need it to do.
And so that Pintle can be a source of throttling.
Yeah, it depends how you design the Pintle, but it's a good choice to design, for a deep throttle injector.
Because obviously the lunar lander engine used a Pintle injector, and it allowed for quite deep throttling, if I recall.
Yeah, and then one of the nice things about it, and Merlin uses the same thing, is you basically use phase shutoff, which gives you a nice, very crisp shutoff. And so one of the downsides of this architecture is when you think about shutoff, if you don't shut off one side before the other, or it's not crisp, then you get a moment, and you're gonna have to It's not the end of the world, right? We'll have RCS on the whole thing and
Yep.
just correct it. But
Yeah.
we do want a nice, very clean shutoff. Helps with insertion accuracy and other things you need out of the
Right.
upper stage. So yeah, the Pinto allows you to do that.
Okay, let's talk about this a little bit too. Stoke will be steering the upper stage, both during ascent and during landing, by using what's known as thrust differential. So instead of swiveling the engines to steer a rocket, if you have multiple engines, you can increase or decrease the thrust on one side of the rocket or the other to actually steer it. Now in Stoke's case, there aren't actually multiple engines. Now there'll eventually be 30 thrust chambers, but they're fed by a single turbopump system, which technically makes it one large engine. So they need to find a way to throttle the individual thrust chambers. For this, you can use what's called a pintle injector, which is not only in charge of the mixing of the fuel in the oxidizer in the combustion chamber, but a face shutoff pintle can actually be used to throttle the engine. This is the same system that the Apollo lunar module descent engine used to deep throttle. The pintle injector has the advantage of maintaining the proper mixture ratios throughout the throttle range, which helps make it very safe and effective. And importantly, when you're dealing with thrust differential control, your throttle actions need to be quick and precise. Now, a turbopump can often be too slow to spool up and down for precise control, but Stoke can operate their pump at a relatively constant speed and vary the thrust individually on every single chamber. And as Andy mentioned, it can also help ensure a nice, crisp shutdown too.
On the booster, where are you guys at actually in that process so far? How far along are you?
We're starting to build and test hardware at the component level.
Yep.
So all of our component facilities are over here. We've got 2 test turbopump test cells. We've got our combustion devices test cell, finishing up component test cell for first stage hardware, and ready to go on that one too.
Wow.
So
Like,
we'll
what's your estimate for when you hope to have a completed first stage engine?
I think you'll see it come together similar to the way Raptor came together, where we're going to test a lot at the component level, and then we're going to do, I guess, what we're calling a breadboard engine. They did one that was, well, it was basically like a subscale demonstrator based on, not based on, but similar to, I guess, Merlin type hardware.
Yep.
We'll do a similar style breadboard engine as well, and then we'll assemble it all into a real package.
And it's going to be, that's going to be closed cycle. Is it
Closed cycle, yeah.
closed cycle? I assume oxygen rich. Closed cycle.
No, we're gonna go all the way. We're gonna do full flow.
Are you serious?
Yeah, I think, you know, look, our
What?
team's got a lot of experience. Any engine is hard, and you want to build the thing in with the highest margin so that you can run it over and over and over again. And I think,
Wow.
full
So
flow
you're
does
hoping
that.
to be, at this point, I'm trying to think of, yeah, I mean, that would be the third full flow stage combustion cycle engine ever built. Or, I
it
guess,
the third?
the powerhead. There's the powerhead demonstrator.
Yeah, the IPD.
Yep. So I
Yeah.
guess kind of in a way the fourth. You might be, and then the second engine to fly. Leave the
Yeah.
testing, because there's the RD270
Yep.
is
Yep,
the
yep,
other,
yep,
the
yep.
powerhead demonstrator, Raptor.
Yep.
And then you guys are going full flow.
Going full flow.
What the, hang on, they're going full flow, baby. I mean, so far this shirt's been fairly representative of very few engines, but you
Yeah.
guys are really, I mean,
this we sat there and debated this for a while, but what we're trying to do, it's the right answer. Every engine is hard,
Yeah.
and every engine is going to take a lot of investment and time, and I think that I'm
But
not convinced it's actually. If you design it, again, it all depends on design decisions, but you can design it where I think it's not too much harder than anything else, right? It will be harder.
Yeah. But it's also in a way easier on a lot of the parts.
Yeah, that's the point,
especially
right?
like thermally through the turbines and stuff. Like you.
That's the point, exactly.
So in a way, you almost don't have to design quite as and spend as much time doing insane,
You're not taking it up all the way to the limit, right? You don't
Right.
have to, right? You have that inherent margin built in, and then over time you can upgrade up thrust and things like that. and you have that margin to be able to do that. So
That's so cool. Oh, well, that's going to be amazing. Well, thank you so much for all your time. I mean, this has just been amazing, and everything you're working on, it's gotten me, as you can tell, very excited. This is really, really cool. Thank you for letting us share what you guys are working on with the world. It's amazing.
And thanks for coming out and helping us tell the story.
Yeah, it's my pleasure. It really is my pleasure.
Thanks so much to everyone at Stoke Space, and especially Andy for all of his valuable time, and for letting Ryan Chilinsky and I come out here and film this interview and engine test. It was absolutely a dream come true, and I am so excited to watch this company continue to develop their system. But I also owe a huge thanks to my Patreon supporters for helping make content like this possible. If you want to help me continue to do what I do, head on over to patreon.com/everydayastronaut. And while you're online, be sure and pick up some cool merch like our full flow stage combustion cycle hoodie that I was wearing, or grab yourself some awesome dress wear, or our future Martian collection, or our schematics collection, or maybe even get yourself one of our amazing Falcon 9 model rockets by heading over to everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.